guys, welcome back. This is example S. This is another mole-to-mole conversion. First, we're going to start by writing the balanced equation. Now, this is going to be a single replacement reaction where potassium and water react. I'll leave a space for my coefficients when I balance this. Potassium is a solid. We aren't worrying much about the states of matter right now, as we've already covered that. Water is H2O. That's a liquid. And they react. It says a gas is produced. So what do you think the gas is in this equation? Well, if potassium is a positive ion and water dissociates into hydrogen and hydroxide, then the potassium is going to replace hydrogen in water and bond with hydroxide, so we'll have KOH, and then what's remaining is hydrogen by itself. Now hydrogen is a diatomic molecule, so that is H2, and hydrogen is a gas. Potassium hydroxide will be aqueous, AQ. Now let's balance this equation. Again, remember that hydrogen is diatomic because it has one valence electron and it shares its valence electron with another hydrogen atom. So that is H2. So we have one H2 molecule here. We have potassium here. We have water. And we have potassium hydroxide. Now to balance this, I have one potassium in the reactants, I have one in the products, I have two hydrogen in the reactants, and I have 1, 2, 3 in the products. And then for oxygen, I have one in the reactants and I have one in the products. Now, I'm going to go ahead and show you that hydrogen is in two places in the products. This subscript here 2 means whatever coefficient you put here will always give you an even number of hydrogen atoms. And here we have an odd number, one hydrogen. So in the reactants, we have a 2 as a subscript behind hydrogen. So again, this is always going to give you an even number of hydrogen. So we need to make this coefficient here an even number so that when we add it to this amount of hydrogen, we still have an even number. We'll put a 2 here. So now I have 2 molecules of potassium hydroxide, and that means we need to balance the hydrogen over here. Now if I have 4 in the products, I'm going to put a 2 here to give us 4 hydrogen in the reactants. Now I have 2 potassium in the products, so I need to put a 2 as my coefficient in front of potassium. And now it's balanced. Let's double check. 2 potassium, 4 hydrogen, 4 hydrogen, and 2 oxygen atoms and 2 oxygen atoms. Let's try a question. You always have to have the balanced equation first because you're going to need that molar ratio between reactants or products or reactants and products together in order to solve these stoichiometry problems. Question 1, how much hydrogen is produced if you have 0.04 moles of potassium? So we're looking at hydrogen and potassium. And here we have a 2-to-1 ratio where we're always going to get half the amount of hydrogen out of this reaction as we put in moles of potassium. So you can see that 0.04 is quickly going to become 0.02 or half the amount of hydrogen. Let's show the math. So we have a mole-to-mole conversion that requires one conversion factor. There are 2 moles of potassium used for every 1 mole of hydrogen gas produced. And there's that 1/2, so 0.04 times 1/2 gives us 0.0200 moles of H2. Let's try another question. How much water is needed to produce 9.7 moles of potassium hydroxide? So now we're looking at water, how much water is needed in moles here. We're doing a mole-to-mole conversion. to produce 9.7 moles of potassium hydroxide. Notice there's a 1-to-1 ratio here, so if you put 2 moles of water into the reaction, you're going to get 2 moles of potassium hydroxide out. So that is an equal amount in moles. So if we put 9.7 moles of potassium, if we get that out of the equation, that means we're going to get 9.7 moles of water and use that as a reactant. If you wanted to show that using a conversion factor, this would be a 2 and this would be a 2, and you'd be comparing water and potassium hydroxide.